The paradox was engineered into the system from the beginning, a technological mechanism designed to defy the exponential cruelty of the rocket equation. Two stainless steel rockets, identical in form, meeting in the quiet vacuum of low Earth orbit not to deliver human cargo, but simply to trade propellant. This refueling architecture demanded that tons of liquid methane and oxygen be transferred between two floating vessels in weightlessness, eliminating the complex machinery of pumps and motors that define terrestrial fluid handling. The core challenge was not in the sheer volume of the fuel, but in the inherent instability of moving cryogenics without gravity to anchor them. A simple exchange that looked perfect on a whiteboard, yet faced immediate collapse under the non-negotiable laws of physics. The Starship refueling system transcends the definition of a mere aerospace experiment. It represents a fundamental attempt to redefine orbital logistics, transforming a disposable launch vehicle into reusable space infrastructure, a pipeline designed to operate beyond the atmosphere. The architecture begins at Boca Chica, Texas, where the tanker variant, Starship 39, lifts off carrying approximately 1,200 tons of liquid methane and oxygen, cryogenically chilled below the threshold of 180 degrees, propelled by 9 Raptor engines that generate 16 million newtons of thrust upon ascent. The impressive destructive power required to escape Earth's gravity contrasts sharply with the delicate precision demanded by the orbital convergence, which requires the two massive vehicles to close distance at velocities measured in centimeters per second. This alignment, guided by redundant radar, LiDAR, and optical sensor arrays, is a collapse into a material problem governed by absolute and unforgiving tolerances. Every latch must align within a span of millimeters, and each valve must hold under a 6-bar differential pressure across walls subjected to extreme cryogenic temperatures. To induce the propellant transfer without mechanical pumps, engineers rely on a seemingly trivial dynamic adjustment known as a settling burn, creating the necessary condition for flow. Both starships fire minuscule thrusters for just a few seconds, generating a gentle, sustained acceleration of about 0.1 ms2, a force so slight it barely registers but is enough to make the free-floating liquids drift down toward the tank bottoms, manufacturing gravity where none exists. With the liquid settled, the tanker raises its internal pressure by a mere 0.5 bar above the receivers, pushing the cryogenic fluids through stainless pipes in a process entirely dependent on autogenous gas flow and pressure differentials. However, the mission operates under a strict time budget, defined by the relentless cycle of boil-off and orbital day-night shifts, a clock that runs continuously while engineers grapple with control problems they cannot tune by feel or intuition. The decision to use cryogenic methane and oxygen for in-orbit refueling introduced a unique physical anomaly, moving beyond the storable fuels of earlier programs. In the hard vacuum of space, any vehicle surface above 100 Kelvin essentially operates as a heater, turning every stray watt of energy into a profound threat to the integrity of the fuel, where even diffuse sunlight can elevate the tank temperature by half a degree per minute. To compensate for this environmental heat soak, the system relies on thermal stratification, a temperature gradient that forms between layers of liquid in microgravity, which sensors must struggle to track for control purposes. The true source of hidden systemic risk is structural thermal asymmetry. When the liquid separation fails, flow stalls immediately, initiating a sequence where the pressure rises, the seals strain, and the system begins to chatter. The critical mechanical failure point is termed vapor ingestion, which occurs when gas rather than liquid enters the transfer line inlet, a condition survivable for mere seconds but guaranteed to be fatal after minutes. This sudden phase change creates a pressure hammer in the lines, demanding that the control software detect the anomaly and command a resettle burn with extreme immediacy, a maneuver constrained by the 2-second processing delay in telemetry, which is the definitive measure separating fluid stability from structural collapse. The narrow margin for success is ultimately governed by pressure equilibrium across the transfer line, which demands that both tanks remain within a critically tight band of +0.2 bar for the flow to remain stable. Should the receiving starship's tank temperature increase by a single Kelvin, vapor expands by 0.4%, an increase that is mathematically sufficient to equalize pressure, bringing the propellant transfer to an immediate halt. If controllers overcompensate for this halt by venting gas too quickly, the flow direction can invert entirely, a phenomenon known in simulations as reversal, where the gentle refill transforms into an accidental, uncontrolled discharge. With the flow oscillating, the liquid columns begin to cavitate, and the two starships operate not as independent vessels, but as highly coupled oscillators, their internal fluids sloshing wildly out of sync. Telemetry from prior tests showed pressure fluctuations rising 40% above nominal values within only 22 seconds of initial imbalance, a dynamic capable of driving mechanical resonance in the feed lines, which is the silent killer of valves and weld seams. The commitment to side-by-side docking also introduced a structural tension in the nose cones, requiring them to handle substantial torsion loads that, if a single clamp fails, could generate a shear force exceeding 120 kilonewtons, leading to a slow, silent venting of cold gas. The multiplication of risk is further amplified by the ambitious launch cadence required for a deep space mission, which commonly demands 8 to 16 tanker flights per mission to amass the necessary propellant. This is not a simple repetition of success, but an exponential multiplication of failure opportunity, as the system is judged not by one error, but by the product of many small errors. The mathematics are indifferent to optimism. If each individual step in the process holds a 99% reliability, 16 repeated steps pull the closing mission reliability down to only 85%, demanding an acceptance rate near 100% for the entire sequence to close the mission tree. The cascade of failure often begins with the thermal environment's influence on the transfer line itself, which undergoes a continuous warm, cold, warm progression as the two ships transit into and out of the Earth's shadow. The system cannot guarantee a continuous column of liquid at the inlet, meaning the first slug to reach the line may be vapor rather than the necessary liquid, an issue compounded by an error in ullage control. This slug of vapor arriving against the warm metal of the line flash boils and produces a pressure spike that registers in milliseconds and kilopascals, creating a hammer strong enough to crack a chilled brittle valve seat or a cryoflex joint. The resulting leak does not manifest as a dramatic rupture, but as a subtle weep, a localized frost ring that begins to grow around the flange, requiring the automated system to pause the transfer for diagnosis. During the mandated pause, the autogenous pressurization system continues to operate, bleeding warmed gas back into the tank to maintain pressure, which raises the gas temperature and causes the boil-off rate to rise by grams per second, a background loss that accumulates to tons across an entire campaign. Engineers quantified the required margin of near avoidance by calculating that a heat leak reduction of only 5 to 10 watts per square meter, achieved through better insulation or sun shields, would have kept the ullage gas cooler. This small reduction in parasitic load would have purchased minutes of extra ullage control and hours of reduced venting, demonstrating that the system was only a few watts and millimeters away from having the necessary reserve. The fundamental insight payoff is the realization that the complete system failed, not because docking, transfer, or thermal control was individually difficult, but because all three phenomena were forced to obey the same unforgiving control volume. The precise causal architecture dictates that the materials and geometry of the side-by-side dock establish thermal gradients when sunlight and shadow alternate, setting a baseline for seal compression that is marginal in one thermal condition. The ullage settlement logic then commands millage accelerations to hold the liquid-free surface against the outlet, but thermal shifts and slosh approximations allow the pickup to ingest a bubble for a fraction of a second, which stresses the already marginally compressed seal, turning a micrometer of gasket motion into a loss-accumulating pause. The essential vulnerability lies in the combination of pumpless transfer, side-by-side docking, and the relentlessly high cadence, which together remove the operational slack that ground-based fluid handling enjoys. On Earth, human instinct can compensate for cavitation or a cooling line. In orbit, this managerial safety net is removed, and physics, exact and instantaneous, decides the outcome in milliseconds. The logic of consequence is absolute. The valves report, the pressure rises, the liquid recedes, and the control loop executes the instructions it was given, rendering the result a product of pure indifferent logic. The institutional response is therefore a mandate to implement deeper multi-layer insulation, MLI, aggressively design sunshields, establish attitude regimes that bias shadow over critical line hardware during transfer, and refine ullage control with real-time sensing of the free surface position. The control logic must become two-phase aware, recognizing vapor ingestion immediately to retract valves before the pressure hammer can form, and seals must be redesigned specifically for differential expansion under asymmetric heating. By reducing effective heat leak from, for example, 35 Wm2 to 25 Wm2 on the methane tank, engineers claw back margin, recovering kilograms of precious fuel over a 4-hour campaign. Yet, even after incorporating these lessons, an unresolved margin remains, an uncertainty lock that keeps engineers focused on the future vector of risk. The optimal structural geometry for long-duration cryogenic transfer remains a question. Whether side-by-side docking is superior to tail-to-tail, given the competing requirements of sun angles and structural load paths across hours. The absolute lower bound on achievable heat leak remains unknown for a reusable stainless steel tank with numerous penetrations, especially as multi-layer blankets inevitably fray and seams age over years of cyclical use. No simulation can accurately predict the long-term fatigue or the subtle micro-gravitational interactions that will emerge when dozens of tankers begin to dock in sequence, turning a few small errors into a cumulative, fleet-scale problem. This is the silent contract every engineer signs, acknowledging that while they can calculate every pound per square inch, simulate every orbit, and rehearse every contingency, the final judgment rests with reality. When the numbers cross the zero-tolerance line, the universe does not display anger or drama toward human error. It merely acts in quiet, absolute obedience to its own laws. The Starship refueling system, in its attempt to unlock an interplanetary future, remains bound by the same law to perpetually test the definitive line between what humanity can design and what physics will ultimately allow.